combination. Atomic combination, matter's cool, it's made with molecules. And did you ever think about the molecules? The bond is very cool, very, very cool. The stars and planets are made of an atom combination. And those atoms are so tiny that you never see them, like hydrogen and carbon and oxygen.
Alright, so for this video, we're going to talk about atomic theory. Rather than just talk about what we know now, we're going to go in depth with the history of the atom and how we got to where we are now. So we're going to start off with the Greek philosopher Democritus. This was really the first time anybody had an idea of something like an atom, basically an indivisible component of matter, just like a building block, a piece that everything's made of. So he had this idea of an atom, although that's not what he called it at the time. His idea was very different than what we know now. What the Greeks thought is that everything, all stuff was made up of 4 different things: earth, wind, water, and fire. Those are the 4 elements, and that's what everything was made of. It's also a pretty good funk band. So that was the idea for really a long time. We didn't have a whole lot of scientific advances for over 1,000 years there, really a couple thousand years, until about 1661. This guy named Robert Boyle, he had an idea that rather than earth, wind, water, and fire, objects were made up of particles that he called corpuscles, and he published it in something called The Skeptical Chemist. So he's thinking there's these little tiny particles, and it's more broad than earth, wind, water, and fire. So this was the idea for a while, until 1789 in France. This guy named Antoine Lavoisier discovered that certain substances cannot be broken down further, just like Democritus had hypothesized. So this guy Lavoisier is taking different substances and doing different experiments to try to break them down and simplify things. He actually discovered oxygen that way, by breaking something down. But he's getting these certain substances that he cannot figure out how to break down. There's no way to do it. So he gets the idea that these are those things that Democritus was talking about, that you can't break them down. That's like as simple as you can get it, these basic building blocks. So these particles that Lavoisier is discovering here are what was eventually called atoms. So in 1805, just about 20 years later, an English philosopher, scientist, whatever, John Dalton, discovered that atoms react with each other to form chemical compounds. So what he did was, he's doing chemical reactions and seeing that these atoms are bonding together to make everything. But what's really important that he noticed is that they seem to react in the same ratios every time. So if we look at this molecule here, if we imagine red, white, and black atoms, we don't really need to know what they are yet, but red, white, and black atoms. If he takes these 3 substances, the red, white, and black atoms, and mixes them together, they always form the same compound, or this is what he observed. So it's the same ratio. You always get the same number of black atoms per number of white atoms, per number of red atoms, and so forth. So he's thinking, well, that must mean that all red atoms are the same, that all white atoms are the same, and so on. And this is why they react the same way every single time. This is a pretty good breakthrough too. So about 100 years later, we really got our first breakthrough as far as learning things with atoms. A guy named J.J. Thompson discovered the electron, another particle that's actually smaller than the atom. It's within the atom, and we call that a subatomic particle. So according to Thompson, these negatively charged electrons are really, 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 really tiny, so small that we don't even really count them. Way smaller than an atom. And they're just kind of floating around inside an atom, in what he called like a sea of positive charge. I'll show you a picture in just a second. And this positive charge was there to balance out the negatively charged electrons. See, we got the negative electrons, but we know that an atom's neutral, so we have to have positive coming from somewhere to balance it out. So Thompson's model is what eventually became known as the Plum Pudding model. Really weird, I know, but they're British, so, But anyway, electrons are basically like plums floating around in a pudding of positive charge. So let's look at a picture. So we've got these little electrons that are, in this picture they're actually drawn a lot bigger than than they would be if it was drawn to scale, because electrons are extremely small, and Thompson knew this. But they're basically just floating around in this sea of nothingness that's just a random positive charge. He didn't really know much about it, but this is what his hypothesis was, and this was the popular model for a long time. This was the accepted idea. It was a pretty big breakthrough. So about 20 years later, this guy named Ernest Rutherford, he was one of J.J. Thompson's understudies, actually learned from him, grew up working for him, so on. He designed an experiment to try to support Thompson's theory. He wanted to corroborate the Plum Pudding model, show that it was probably right. So his idea is to fire these things called alpha particles. He didn't know much about them at the time either, but he knew that they were really, really tiny particles. He wanted to fire them at a thin layer of atoms to prove that they would all pass through the pudding since electrons were so small. So basically, here's the idea. If we've got our model of an atom here according to Plum Pudding, all right, we've got this sea of random positive charge here with little blue electrons floating around inside. And again, they're way, way smaller than they're drawn here. So small that they basically don't even matter. So what his plan is, he's going to fire alpha particles straight through, and the pudding is nothing, so it's not going to stop it. It's going to go right through that. And the chances of it hitting an electron are like zero, basically, because electrons are so small they don't even matter. So he's thinking, I'm going to fire these alpha particles at a sheet of atoms. It's just one atom thick. So one atom thick, and he's going to fire it at it, and it's going to go straight through because there's nothing to stop it. So he was going to have a detector on the back side, fire the alpha particles, and it's going to hit the detector. So he'll know that it went straight through, and that was his plan. That would support his Thompson's hypothesis. Okay, so here's what really happened. Pretty interesting. He's got the alpha particle emitter that fires the alpha particles. It goes down a beam and hits the sheet of gold foil that's just, again, one atom thick. So this is extremely thin here. So he thought it was going to go through, but as you can see in this picture, it didn't. Now some of it did. As you can see, the beam goes through, and a lot of them turned a little bit, but a lot of them are bouncing off and deflecting here, which is not what he expected. Way, way, way more deflected than he expected. So basically what this means is there's something there that the alpha particles are bouncing off of. Something there that he did not realize was there. So Rutherford's idea is, fire these alpha particles, thought they were going to pass straight through, and a lot of them did, but some of them bounced off. So what his idea is, this positive charge that we know is there, rather than like a random pudding that's just kind of spread all around, he's saying there's actually another subatomic particle in the middle. And when we're firing these alpha particles, a lot of them are passing through, but some of them are bouncing off this positive charge, wherever it is. So Rutherford's idea became what was eventually called the nucleus. So this picture here is basically the Rutherford model. All right, we've got a positive nucleus in the middle with little negative electrons floating around it. This was a pretty big breakthrough too, and the Rutherford model is actually pretty similar to what we have now. We know a lot more than he did about specifics, but this is the general idea. Positive charge in the middle in the nucleus with negative charge floating around the outside of it. So, like I said, basically right. The positive charge is in the middle in the nucleus, called protons. There are also some neutrons there in the nucleus, just packed together. Around the outside, you have electrons orbiting around the atom, just like, orbiting around the nucleus, just like planets orbit around a star or something. And like they thought, these electrons are basically massless, so small that they don't really even have a mass. Alright, so let's zoom through this really quick. These are some details about what we know today about subatomic particles. So first, we have the electron, negatively charged, orbiting around in the electron cloud at basically the speed of light, really, really fast. Second is the proton. Protons are positively charged, located in the middle in the nucleus, and they are 1,836 times bigger than an electron, mass-wise. So this is why I'm talking about that electrons are so small they basically don't even matter, because protons are that much bigger. Last up is the neutron. It's a neutral charge, hence the name neutron, and it is also located in the nucleus. It's the same size as a proton, as you might notice. Again, way, way bigger than an electron. Okay, so here's a new vocab word for you, nucleon. Nucleon just means something in the nucleus, which is either a proton or a neutron. So when you see the word nucleon, it just means proton, neutron, or both. So, when you're getting the mass of an atom, like we said, electrons don't matter because they are so small. They don't matter in terms of mass because they're so small. So all you got to do is add up protons and neutrons to get the mass. So the mass of an atom is just the sum of the nucleons, protons and neutrons. Here's just a nice data table for you to put it all together. If we look at the mass in grams of each particles, you see what I'm talking about, how ridiculously small they are? You would need 23 zeros before the number on a proton to get the mass in grams. That's way too small to want to deal with. We don't want to work with those numbers. So we created a new unit called the atomic mass unit, AMU. The atomic mass unit here is what we measure mass in. Way easier to deal with because the mass of a proton is 1, the mass of a neutron is 1, and the mass of an electron is so small compared to the mass of the other two that we just refer to it as 0. So really, this is 0 as far as we're concerned. Okay, charge. Again, there's a unit called the coulomb that we measure electrical charge in. Protons, charge is here. Electrons, charge is here. Again, not really pretty numbers to work with, so we made up our own unit. Protons are a positive 1, electrons are a negative 1, and neutrons are neutral or 0. Alright, quick rapid fire questions here. The electron cloud is the region of the approximate location of electrons. The reason I say the word approximate is because they're orbiting so fast that they're really never in one place at the same time, and we can never be sure exactly where they are. We draw it that way in pictures just because we have to. Okay, if we're talking about which part of the atom weighs the most, it's got to be the nucleus. In fact, the rest of the atom basically weighs nothing. The electrons weigh just a tiny amount, but as far as we're concerned, it is nothing. The last part, 99.999 lots of nines % of an atom is actually made up of empty space. Okay, you've got that nucleus there in the middle, just protons and neutrons, and then way, way out here, you probably can't even see these dots, okay, around the outside. The electrons are far away, and in between here, you've got a lot of empty space. Imagine something like a grain of sand floating in the middle of a classroom. That would be the nucleus. All of that space in the classroom is just empty space. Kind of weird to think about atoms, like the atoms that make you up, being mostly empty space, but that's how it is. The only reason that atoms can't pass through each other is because all atoms have an electron cloud, right, going around the outside of them, these electrons. And electrons are, flying around, orbiting really fast, and they're negatively charged. So when two atoms get close to each other, those negative charges are going to repel each other. So really that's the only reason atoms don't pass through each other.